today I'm going to share part of my master thesis, mostly experimental part of my thesis today. So my presentation will include 5 main parts. First of all, I will give a brief information about the well concept in the fatigue testing, also applications. Then we will talk about briefly on literature overview and what is the motivation of our work. And then I will give information about how we did the tests and plan it, and then we will talk about the results and relation and summary. We can continue. So, as may be all familiar with the sustained peaks, holding times on the different engineering application. This mostly represented by the well term. For example, in here we have a rough mission of a aero engine. In here you can see the well periods roughly in sustained holds like, and it is actually can be simplified as this graph, in which we see that at the peak level of loadings, there can be considered as a dwelling holding for at higher stresses, and most of the literature works also considers is in the cruise form of the engine cycles. So we can move on. So the literature array, when we look at the early stage of works and the recent works, we see different approaches. For example, in early stages, we see that the interruption of the fatigue loading, mainly made in 1950s to 1980s, in which in the steels and also in the nickel alloys, they observed the increase in fatigue life. That's made because of the strain aging, stress relaxation, and oxide-induced crack suppression. Strain aging and stress relaxation mostly observed in the steel materials, but also in nickel alloys they observed oxide-induced crack suppression in terms of interrupting the fatigue loading. And the early stages of the well fatigue works on is actually focusing on initiation cycles, and later on the recent works in the literature are more focusing on the propagation cycle, and in that term they mostly perform a fatigue crack growth testing in order to understand how the crack rate changes during the hold times. We can move on. Next slide. So overall in literature we can say that if the well affects change with temperature, the well time, loading rate of course, and so on. In that cases, mostly recent works showed that with increasing temperature and with increasing the holding times, crack propagation rate increases. But in terms of mixed load test, where you not applying the higher load device holding times, instead of that, you perform some certain period of cyclic loading, and then you hold the loads at peaks and so on. In that case, it's actually depending on the delta K, which is load that you apply to material itself. So, and also in the literature, these all approaches are performed in the mostly axial tests. So there is a uncertainty about if the loading condition change, bending, torsion, etc. How is the well affected the initiation lives and the overall fatigue performance of the material. We can move on. So in our experimental procedure, we divided our work in mainly two categories. First, mechanical testing, then characterization. In mechanical testing part, we performed room temperature, high temperature, rotating bending tests at constant amplitude, and after that we applied the wells between the cyclic loading periods at both room temperature and high temperature in order to see the effects of it. And after that, in order to understand the phenomena, we perform some surface roughness measurements, microstructural monitoring, SEM monitoring, also the hardness and non-indentation testing. Next slide. So, what we used in our tests, we used alloy 718, AMC 5663, extracted from longitudinal direction from forged bars, and we machine our specimens according to ASTM 466 and netcap code Z, which is some consortium defining the requirements of the mechanical testing in the aviation industry. So in that case, our specimens has a roughly surface roughness value as 0.2 and has a compressive stresses at the surface and the subsurface, but these are relatively low compressive stresses, and we have these values for all our specimens. And also we measured the grain size before starting and after the tests with grain size, just to see if there is a change or not. And our initial grain size is ASTM 8 to 10. It's about 16 to 11 micrometers per grain. We can move on again. So we did our tests, as I mentioned before, rotating bending. In here, I would like to impress some testing part of our work. I mentioned that we performed a high temperature test too. So in that case, in order to understand and in order to make sure if we have the correct temperature form at the specimen, we perform some temperature profile before the tests, and after the temperature profile, we saw that the best way to get the testing temperature, which is 450 degrees, is 2 steps, and between these 2 steps we apply some soaking time in order to homogenize it, and so on. Total soaking time and heating time is about 90 minutes for each specimen. We can continue. So in here you can see the raw data from our tests. We have coupled runout data in here, and we performed our tests approximately about 70% UTS to 35% UTS of the specimens at room temperature, and it's about 60% UTS to 40% UTS at high temperatures. We can see in here that there is a little scattering here, but the higher stress values looks fine. We can continue. So when we calculate the best fits in order to compare the trending of the tests, first we compare the room temperature and high temperature not well applied tests, in which we saw that the high temperature tests are a little bit below on the room temperature as we expected, and we use also the basic linear equation for our test results. We may continue again. So in here, what we have here is the orange triangles, and the red curve is our high temperature base curve, base data, and here as blue we have well applied curves. As we can see in here, interestingly, at high stresses, well seems to be not affecting the fatigue life, but in low stress regions, we see that there is a kind of increasing life, but there is a little scattering here too. So it's not certain, but trend-wise we can say that there is a little improvement in life at certain stress levels, certain lower stress levels. We can continue again. And after that, when we see the well sensitivity is depending on the stress levels, we applied the lower stress level room temperature well test in order to see the thermal effect, if there is a effect on that well behavior. Interestingly, we saw a decrease in the room temperature at lower stress values, in which unfortunately we don't have enough specimens, so we only have repeated it 3 times. Maybe with more specimens we will have a more precise result, but from these tests we can say that there is a slight decrease in the fatigue life, even if when we compare with the 95 probabilistic curves of that. We can also continue. So in here we have a NCR graphs. NCR is actually basically the fatigue life divided by the continuous fatigue life. We see that right hand side we have a high temperature comparison, and we are also clearly seeing that the well results with decreasing the stress levels are becoming more and more far away than the 100%, which means the exact same the fatigue life results in here. We can move on. So in order to understand why it may be happened, we performed firstly basically hardness test in order to understand if the material is softened or hardened or something different happened. To do that, actually we prepared our specimens, our fractured specimens, and we measured hardness values from 3 different regions. These regions are basically near the fracture surface and relatively medium range from fracture surface, and the outer regions, which is actually 2 to 4 millimeters, and the fracture surface measurements that we have have distances from fracture surface about 0.15 to 0.23 millimeters. So in here we see that from far side of the specimen to fracture surface we see a softening. Maybe we can't conclude it as softening, but there is a decrease in the hardness values once we reach to fracture surfaces, and this decrease in the hardness is also affected by the applied stress and applied dwell. In here, I can show you that, for example, this black line has a little scatter, but this black line is lower than the. Sorry, this one's the full cyclic, and this blue one is a dual at same stress values. But it seems that once we reach the fracture surfaces, the dual fatigue one is has a much lower hardness values than the other. So once we see that, we just want to learn about the plastic capability of the specimens. We can move on.
Can you be a little faster?
Oh, okay. Okay. So we applied the non-indentation testing in order to see the plastic work capability of the well applied and non-well applied test. In here, interestingly, we see that there is no significant change in plastic work capacity. By the way, we calculated plastic work capacity by just simply calculating the area under the non-indentation curves, and we saw that there is a similarity between them. So actually, it's created another uncertainty. We can move. Thank you. So once we see that results, we actually looked at fracture surfaces and did some SEM monitoring. And in here we saw that at the left hand side we have a specimen fracture surfaces which is not worked under dwell conditions. We can see that the surface is pretty much smooth as we expected from standard fatigue tests. But once we applied dwell, you can see in the micro image here that the topography is changing drastically, and we can see it on macro scale too. We can move on. So once we have the SCM analysis at the higher temperatures dwell and non-dwell tests, however, we see similar features like secondary cracks. This one is non-dwell test, and these two are dwell test. The secondary cracks seems to be increased, but it's not certain. We observe in both cases at high temperature tests. We can move on. And at room temperature, where the dwell fatigue decreases the life in rotating bending condition, we see some different features. For example, at left side, again we have a non-dwell test, which is actually seems pretty normal, has a couple little secondary cracks, but we can see the titration network clearly. But in here, once we applied the dwell, even if at room temperature, it seems that we saw different features. For example, one of our specimens had a fractured in subsurface region that is not that is really an unexpected situation. And once we check the crack propagation side, we also see some brittle behavior that we may consider. We can move on to the last slide. And for summary, what we did some high temperature, room temperature rotating bending test, and after that we applied some dwell during these tests. And with that dwell application, we see that the dwell effect is highly dependent on the stress levels. And in terms of thermal effect, I believe there is some certain effect, but because of the lack of test numbers, I'm not sure of it. There is a little bit uncertainty, but we can say that in rotating bending condition, Inconel 718 at intermediate temperatures like 400-500 degrees seems to be not affected. We can say that the increase in saying that the life increases with the dwell is a really strong quote. So we can say that with these number of tests, but we can say that at bending conditions, Inconel 718 is relatively conservative material in terms of dwell applications. This is the overall my work. I thank you for your attention and happy to hear some recommendations, comments.
Okay, thank you. If anyone has any questions, the quick ones. Okay.
So in the dual testing, the stress level, you said maximum you go up to 70% of yield strength, right?
UTS. 7% of UTS level. But the well tests are applied at approximately 60% of UTS levels. So it's actually not that low, but we started about life regions, which is resulted, for example, it's nearly 10 to the 4 cycles to 10 to the 7 cycles. So we tried to scan a little bit large area actually.
Okay, thank you once again. So our next presentation is titled Fatigue Crack